So it's my pleasure to introduce Ken Baker from the University of Miami, who's going to talk about bounds on Morse-Novikov numbers of three-dimensional manifolds.
All right. Well, thank you very much for the introduction. And it's a pleasure to be here speaking at this conference. So I'm going to talk about this question of Morse-Novikov numbers, three manifolds. And to introduce this, we're actually going to start off with a few toy models, and ones where I think it's a little bit easier to kind of more viscerally interact with and visualize and just kind of get the idea. In fact, there's some kind of equivalent problems there that are, I think, at least ones that you feel like you can do something with, whether or not you can actually get some. And then we'll kind of talk about the more general setting of actually working with three manifolds. So, and I should say, especially kind of the latter part is some joint work in progress with Fabiola Mendes Gutierrez from UNAM, Mexico. Yeah, so rough outline, very rough outline is that we're going to first look at these different toy models of Morse functions and Morse-Novikov functions. And then we'll kind of focus, bring that back around and look at actually three manifolds and some special situations there. I'll maybe say out loud a little bit more broader thing that Fabiola and I have been working with. And then we'll kind of wrap that up with a little bit of a discussion about an interesting function on the second homology of the three manifold that this actually this investigation gives us, and something that allows us to understand some of the properties of this function. Okay, so let's start off with toy models. So I want to think about having a height function on S3, or you can take a standard height function on R3, however you want, and I can think about a knot inside S3. It could be a length you prefer, and I wanted to think that the knot is in some sort of Morse position with respect to this height function. Right? So I'm going to fix a particular Morse, configuration of the knot in a Morse that's Morse with respect to the height function. And then I can look at all the different spots where I have a critical point. And it's being Morse in this situation, we've only got maxima and minima. And what I can do is I can just add up, count how many I have. And in this particular configuration, I have six extreme ones, six critical points. And that's some measure of complexity of this particular embedding of that knot, right? And here I kind of showed it with the map to like R, where I marked these critical points. I think we can maybe toss that around away for the rest. What we can observe though is actually, because we're dealing with knot theory, is that we can actually do some other moves. I mean, first we have more kind of one isometry that you can just kind of rotate this vertically. I rotate about 90 degrees, and that changes the number of critical points I have. I should have like 1, 2, 3, 4, as you see there. And then, in fact, again, this is topology. I can just do like some smooth isotopy. It's not, and actually kind of reduce the number of critical points. In fact, if you're careful, you can see that this is actually an embedding of the unknot, and so I isotope it down to like a nice round circle and put that circle into a Morse position, so that has just one maximum, one minimum, so the total is 2.
So can I think of this as a map for this, a path to the space of maps from S to R, and most of the time you're using Morse functions, but you have some birth and
Sure.
Like in surf theory?
Yeah. That's a great way of thinking about it. Exactly. So you can think of the entire space of these things, and we have these chambers. I'm actually not sure really the technical lingo for that, but you have these chambers where it's constant. This number of critical points is constant, and then you have this kind of wall crossing where you pass through times where you're not in a Morse position that this number may change. And what I really want to think about then is, I would say, just for lack of other words, actually there are other words I will say, but at this moment, let's just say the Morse number of the unknot is 2. I'm just going to count the number of critical points of the Morse function. Now, here's a spot where people might say, well, look, you can just actually lay that circle a little bit more flat, and then you have, you have no, you just kind of have one critical value, or like one maximum level. I'd say, okay, fair enough, you can do that if you want, but I wouldn't call that Morse position. Right? So, yeah, all right, fine, whatever. That's not what I'm talking about.
What the Morse-Smith.
Yes. You said that with the 4 days all let's continue with this and actually get some actual definition. So, so here what I did, I actually changed the crossing now. So now we actually have a legit diagram of a figure 8 line. And here, this position that we have does have 4 critical points. And just to kind of set some notation, I'm going to use script K for talking about the knot type. So, this entire path of embeddings of that presentation of that particular knot, and then I'll use just the regular Roman K for a particular presentation of that one. And so, for a particular knot type, I'm going to look at these knots K. We're representing that knot type that are Morse with respect to our height function. And in fact, this Morse number that I was mentioning earlier actually has a more classical name, which is the bridge number. Okay? And the bridge number of that presentation is just half the number of critical points. Really, we would say maybe it's just the number of maximum. And then the bridge number of the knot type is we just minimize overall the Morse presentation. Okay? So that's pretty. That's very, very classical. And just kind of core examples is that we have this nice kind of uniqueness at the minimum, this property at the smallest that can have for this bridge number, or if you want twice the bridge number is the Morse number here. That's the minimum we can have. The bridge number of knot type is 1, if and only if that knot is the unknot. And then for this example, figure 8 knot we know is not the unknot, and we can verify that therefore it has bridge number 2. Okay, I think everybody learned this way back when they were weak grad students. Not to offense to those who are still weak grad students. All right, so I want to ramp this up and give it more of this kind of Morse-Novikov space where I'm thinking of like circular Morse functions. So here I want to change to thinking about these maps of from the solid torus S1 cross D2, and you just think of like projection onto the S1 factor. So you have all the disks as your level sets of that function. And now I can think of, well, I've got a knot type inside this solid torus, and I can just look at all the all the critical points with respect to that circle value Morse function. Or if you want, all the tangencies with these disks. And in this particular guy, I want to point out that I have like these two, this particular knot, or this particular embedding of this knot in the solid torus, I have like two critical points. And kind of following kind of the lingo that we were doing before, we just call this circular bridge number to be kind of half the number of the critical points. And then the circular bridge number of the knot type, of course, is the minimizing disk. And here's interesting is that at the minimum possible, we can actually have 0, but that's exactly when your knot's completely transversed to all these disks. Well, we know that means, in fact, our knot is be represented as a closed grade. So we get this nice if and only if, and now I've done my due diligence of mentioning grades in this talk. Okay, great. So I think what I really want to I think you should take away from this is that somehow the circular bridge number is kind of one kind of measurement of aberration from being a brain. Think of it that way. So start thinking of like, well, how far away are we from being a brain? So, of course, this works for links instead of knots.
And also think of it as a measure of how far it is from the vibration, the component.
Yeah, we're going to get to that. I mean, so you can think of it as a vibration as well. I mean, that's really
when I switched to three manifolds, that's really how I wanted to think about it.
So those correspond, and the yellow points to some singular factors.
Yeah, so if we're gonna just kind of cut to the chase, let me just go to the last slide. Later on. But yeah, so thinking ahead, one way of kind of getting a connection from is that you can imagine taking the double branch cover of this class, right? And then you're actually going to get the honest circle value Morse function on a three manifold with torus or two torus boundary components. And this is going to give, at least in, this is giving a measurement of how far away you are from getting an actual vibration. So then these kind of max and minima are going to actually correspond to different indices of singular. So you get a nice exact correspondence there. Of course, there, since we're going through the double branch cover, we have this equivariance. That's nice. And in fact, so the reason I'm going through all this is that if you're not used to thinking about the three manifold version of it, it's almost exactly the same kind of story here, but we can actually very viscerally and hands-on look at this and get some interesting results here. So in fact, this lets me bring in, just even looking at this kind of toy model here, we can like look at, I think, what is the key feature of what we're going to be talking about later. So I want to point out here that this particular one I did, if I look at these like level sets, I have like 5, if I look at the minimum number of intersections, I get like, I count 1, 2, 3, 4, 5. I guess over here I would have like 7. If I look at the regular numbers. Now, and for this presentation, then I would say 5 is the rapid number of that particular. The thing is, like, you could actually take this guy here and slip him all the way through, and reduce, get down here just by isotope. Okay, and so we maintain this kind of circular bridge number, while we're reducing the rapid number. In fact, you might notice that you can actually go the other direction and start going very far and preserve this circular bridge number while ramping up and getting arbitrarily large rapid.
And by the way, one more question. Is this rapid number equal to the limiting number of the black circle with the
No, because notice right here, this is a knot, and this rapid number is 3. So if I was to put an orientation on it, I can see kind of, I should put an orientation, but if you put an orientation on it, you can actually see that this has winding number 1. Okay. And in fact, if I was to kind of, make it a little tighter, you might recognize it as like a maser pattern. So I picked that one just because it's kind of should have made it more identifiable as such. But this is one that's known to have a wrapping number 3, a winding number 1, and so it shows that there's something a little bit more going on in this wrapping.
So it's like a geometric number as opposed to algebraic.
Exactly. Yeah, that's exactly what I was about to say. So,
Sorry.
Yeah, no, great. You're doing my talk for me. We should just do like talk karaoke, slides, and you get whatever you say. No, that's wonderful. So yeah, but that's exactly the point. I mean, so there's some curiosity about this wrapping number now, and the fact that we're seeing this circular bridge number, and we know that 2 has got, because we know that the maser pattern is not a graded pattern. We know that in fact the circular bridge number has got to be, I guess it's half that, so it's got to be 1, right? Yes.
So this wrapping number of a knot type, is that bounded above by
Is it bounded above by the grade index? Well, so it's a little funny. I mean, because by asking for the grade index, then all of a sudden I'm pulling outside of using just a solid torus, right? So you would have to choose an embedding of that solid torus into S3, maybe as fixing a braid axis, and then allow yourself to do these Markov stabilizations. And depending on exactly how I drew the Markov, I'm sorry, how I drew the Maser pattern, you would actually say, well, that's when you embed it, maybe it's just an unlock. Right? Maybe it's isotopic to the unlocks would have greater than so on. So that I think it's maybe there's something that could be said along those lines about looking at, you know, this with respect to actually a rate axis and thinking of the, I don't know, there's some directions you could probably go there and say something. But, I think without getting too far afield, I think we should just kind of think, really restricting attention to just knots and links and solid course. But no, that's an interesting idea. Yeah, for sure. See, I think I have this still on this. Yeah, this is what I really wanted to ask about. So this is the yeah, that's why I actually said this. Look, it says not rate. K is not a rate, so therefore the circular ridge number is 1. And the K is, we also know it's not locally knotted. For instance, there's another way of seeing that. In fact, that the graphing index is greater than the graphing index is greater than 1. So you can actually see this. And so what we're seeing here is that, in fact, the wrapping number is being realized by a presentation that also realizes the circular ridge. And I think, surprisingly, I mean, maybe somebody here has some ideas on this, but this question, so fix a knot type in solid torus. Does there exist a presentation of that knot type so that it realizes the circular ridge number and the wrapping? Is that always, I mean, it seems like it should, right? But then you start thinking about really messy guys and like, well, is it? You know, so it's one of these things where I thought there would be an easy proof for, and maybe over all of these mornings that I've thought about it, I haven't had enough coffee. The point is, like, I think this is kind of a fundamental question about understanding these kinds of things. And if you're thinking ahead to the three-manifold question, I'll let you think, well, what do I mean by, what is the translation of the wrapping number when I'm taking a double branch cover? What is this, you know, where are we going with that? So there's an analogous question that we'll talk about. That's an even harder question. So this toy question, I think, is a hard question. Maybe you have an easy answer. I'd love to see it. But I think this would be answering this question just for knots in the solid torus. Answering this, I think, would be very illuminating.
Isn't the by analogy, this would be some kind of perfect Morse function or Morse-Novikov function?
You have to remember.
Perfect means you kind of realize this, you know, the Bethe numbers are realized. You have a Morse function, the Morse inequalities are satisfied with those.
Yeah. I mean, but this.
I know it's by analogy. It's some kind of.
You still need a little bit more. This, if I understand, if I remember what the word perfect means in this context.
Yeah.
And that doesn't encapsulate what's happening with this kind of wrapping issue.
Right.
That's a really separate thing. Perfect just means, if I remember, it just basically means you've gotten rid of your 0 and 3. Right. That's not enough to handle this issue. So very simple. So let's just kind of do one more toy model, just kind of ramp it up a little bit. So now I want to think about knots in a thickened torus. Okay. So in a thickened torus, well, for my torus, I have like this nice kind of, you know, every rational number, I have a slope. And from that slope or direction, I can think of having a circle value Morse function that's kind of just looking across that. So I have there's an example of a knot in a thickened torus, just did a projection of course. And then here's like 2 different directions that. And of course, you have an entire circle of directions, and you can ask about their circular, the number of critical points they have, and their circular ridge numbers. What does that do? I mean, well, I didn't write it here, but the point is, you can think about this as a function of directions. If you want, think about this as somehow telling, you know, this is kind of a nice function on this guy where you see this happening in this entire circle of directions, and there's certain properties that come out of this. I see it on the next slide. Oh yeah, I see it here. So this has nice things. So first of all, you know, the direction where we're going, see it's obviously symmetric that way. And maybe it's not too hard to see. It's so bad to see that, of course, this as a function, this is going to be bounded. It doesn't matter, there's an overall amount. But then I think the kind of maybe slightly non-trivial thing to see here is that this is like a locally maximal function. So if I look at a direction here, and I count the circular bridge number, well, nearby, I'm going to be maybe counting that for that particular presentation. Say K realizes the circular bridge number for this direction. Well, then for that same presentation, as I slightly tilt it ever so slightly, I'm going to get the same critical points as those, those stable. But that particular presentation of K might be able to isotope around and reduce it as I, as I tilt it some. So all I can really say is locally, like in an interval of slopes and a small interval of directions, I know I'm locally. So that's an interesting kind of feature there. All right, so I think that is a great model. See, we're out of time. Okay, not so bad. All right, so now I want to pass to just a more general three-manifold side of just the circular course. So I've got a three-manifold compact and oriented. To keep things, the discussion simpler here, I'm going to restrict to having the boundary of our manifold be chloride. You can actually, of course, do it for higher genus boundary components if you want. You have a little bit of issue of, well, what should this circular, what should the restriction of the Morse function on the boundary be? So one of the things that Fabiola and I have been doing is saying, well, if you have a sutured manifold structure, then that kind of tells you what to do, in terms of looking at these things. So we have a nice way of thinking of, you can just have a sutured manifold structure to kind of understand your Morse structures and circle boundary structures. Today, I'm just going to keep it simple and assume our boundary are just chlorides. That illustrates the main features. Then we're going to assume that we have these functions, from our three manifold to the circle, and I want to, like we were dealing with knots, I'm going to restrict the ones that are Morse. And then I want this kind of word, there's various words I can use, but I want it to be regular, meaning that when you're looking near like a collar boundary, these boundary chloride, you kind of got this nice kind of decomposition where the level sets are all these kind of nice annuli kind of coming into boundary, nice structure way to like it to be. So funny stuff. Yeah.
Talk about Morse functions.
So the way I like to think about Morse, is that all of your critical points are locally quadratic. So basically, you think back to your multivariable calculus. You've got your A singularity is a cap, the cup is your maximum and minimum. For your, we're in three manifolds. I'm just doing that on surfaces. So then we have the kind of main point is you have this nice correspondence. We'll get this nice correspondence with the 0, 1, 2, and 3 handles, right? And in fact, we'll get to that. That's how I prefer to think about it.
Okay, sorry, my mind wandered a bit. So do you require this Morse function on the boundary to be a standard projection on one of the coordinates?
Yeah, exactly.
I you said it, but I didn't.
That's what I'm kind of trying to. I didn't say it that way, but that's what's happening. Yeah. So in fact, I wanted to have on a collar, just so we have some nice weight there. So that's what I was meaning by this word right there. You don't want any kind of funny business going on there. And then what I said even before that, I was talking about higher genus boundary. Is that in fact we can adjust that to be something different, and it's still a super manifold structure on the manifold. So if we have talk about spots that are supposed to be kind of a R plus and R minus, and then we have these annual sutures or toroidal sutures. So that kind of tells you what the Morse function should do to the boundary. So we'll have these, kind of think about it as a manifold of corners where like these annular sutures are kind of kind of foliated by the circles. And then the R plus, R minus kind of like level sets. Plus has the transverse vector pointing outwards, and R minus has a kind of get this nice. You can kind of generalize all this immediately once you kind of fix that kind of structure.
But for now, the boundary is just right.
Yeah, just because it's easier to talk about, and bringing in the sutured manifolds just forces us to have to deal with a lot of extra notation, and doesn't really. I mean, there are some spots if I was, where maybe it's kind of convenient, but it doesn't really offer a whole lot to getting to that. So in particular, like the fundamental examples of these kinds of manifolds are the exteriors of Nonsymmetrical links in S3. But you don't have to restrict to Nonsymmetrical. There is a little qualification that I'll mention later, and I'll wait for somebody to ask it first. But I want to point out here that these functions, these are circle value functions, so they're a homotopy class. Right? You can just think about that function being a member of a homotopy class. So I want to think about this as kind of analogous to a particular presentation of the knot inside a knot type. Right? So this is a circle value Morse function inside a homotopy type function. And then we know that there's this nice kind of correspondence with the first cohomology, for these classes, and then point radiality or whatever. We did an isomorphism with the second homology. So basically, what's happening here then is that the level set of this function is the surface representing this class. So I actually like to think in terms of this guy a little bit more than thinking about these other ones. That's my preference, but it's kind of the same.
Just one more question, I'm sure. So you look on the top of Morse-Novikov now, in a sense, right? You could count only the points of index I. You could find this. But
yeah.
Would that be interesting, or because you want 5 classes, and you just think about the top of them?
So let me repeat that question. So here I've been talking about just counting the number of critical points, just total number of critical points. And then the question was, well, look, why don't you refine that and count the index 0 critical points separately, and we count the index 1, and count the index 2, count the index 3. Do that. When I have boundary that's just tori in particular, with that where these functions are of this sort, it actually turns out that you can always cancel the 0 index. If I'm trying to minimize everything, I can always cancel the index 0 guys with some index 1 guys. So I can always, if I'm going to try to minimize things, I can always get rid of my index 0. Then kind of in a dual situation, I can always cancel the index 3 with the index 2, right? So all of a sudden, I can assume that the index 0 and index 3 are, well, there's none. Now I'm left with just index 1 and 2. Well, just like we saw in the knot case, they're in balance, so you have the same number. So this is a special to 3 manifolds.
But in particular, then this number is even.
In particular, this number is even. For this kind of setup, I mean, if I allow different genus boundary, things can be a little bit imbalanced, and especially when I start doing super manifold, we can kind of get some things funny in it. But yeah, this is kind of more classical situation with this Morse-Novikov number. Those numbers are always even, kind of like the original results. Yeah. So right, great. And then we've had plenty of time to read this
feature that was already pointed out to us before, that in fact, this Morse-Novikov number is 0, if and only if this function is actually described by a vibration. So I would say that the second homology class here is a fiber class, borrowing terms from like the version norm. Yes. All right, so. And then, well, this kind of looks a little bit at that I said. So I want to kind of point out that we can talk about rules for nonsense links, and Pagitnov, Rudolph, and Weber, I think first kind of seems like they're the first ones that kind of really identified that there's something to do here in terms of three manifolds and do for nonsense links. So they had this paper from like late 90s, I guess. Where they did a lot of the basic groundwork and looked at the homology about certain bounds and interesting, just kind of basic information about all this. And what they did when they had an oriented link, you can look at the link exterior here, just the complement of radar neighborhood. And then they focused upon the class that was represented by a cyclic surface. So once we have this oriented link, we have a cyclic surface, class of cyclic surface, a well-defined class of cyclic. So that picked out a very particular class. So they just defined that the Morse-Novikov number, that oriented link, was this, was the Morse-Novikov, what I was calling this Morse-Novikov number with respect to that class. Oriented links in S3 have cyclic surfaces, so this is a well-defined thing. There's some curiosity in that. If you change the orientation on like one component of the link, this could totally change.
Can you remind us, is this class C that you went down, is this the 1111 class in the Meridian basis?
Yes. Yes. It's one that evaluates the one of all variants of so in fact, what was it? 2018 maybe? That's right. How my years pre-COVID. Pagitnov actually visited Miami for about a month in spring and gave a short course on these Morse functions. And he presented this question that came up way at the end of the course. He said, well, in fact, in our initial paper here, there's this obvious inequality. If you want to understand the Morse-Novikov number of dots, well, what the natural operation is connected sum. So, and the natural question is, well, how does Morse-Novikov number behave with a connected sum? And it's not too hard to see that the Morse-Novikov number of the two summands is an upper bound of the Morse-Novikov number of the sum. So I just kind of drew a little schematic here. We've got these kind of two pieces. So this is, think of this as like the exterior K1, and this guy here is like the exterior of K2. And then when you're doing connected sum, they get kind of glued together along this annulus, where the core of that annulus is following that radius of lines. And so you can imagine when you're looking at a circle valued Morse function on for this, you want something that's going to realize this Morse-Novikov number. So that's just something that kind of wraps around here. In fact, it kind of behaves very nicely on near the meridian. And then you've got this thing as well over here. And, you can just kind of like slap those Morse functions together, and it works out pretty well. You get a Morse function on the exterior of the connected sum. And so that's got it where the number of critical points is exactly the sum of the critical points for each of these two. So that naturally gives you. And so then the Pagitnov asked, well, actually, in their paper, they asked, well, is this actually an equality? And I said, of course it is. And the point was that, why did I say of course? It's because I'm a three-manifold topologist, and I'm very familiar with Hagar splits. And instead of Morse functions, they're kind of
gradient flows and all that, I don't think about that. I think about the handle structures. The idea is that your handles, you're the various distances of points, like index 0 and 1 critical points correspond to 0 and 1 handles. Index 2 and 3 critical points correspond to 2 and 3 handles. And the point is that whatever kind of like circular Morse function you get, this kind of ends up giving you a nice way of decomposing your manifold into a sequence of compression bodies. And so we would call this like a circular Hilbert splitting, or because we have several of these around, maybe call it a generalized. So these are compression bodies. Basically, the idea of a compression body is that you start off with a surface, perhaps disconnected, and maybe a collection of 0 handles, like balls. And then you attach, and then you kind of thicken that surface up, and then on the top side of that, you just attach a collection of 1 handles. That's going to give you one of these red. So that's what a compression body is. And then dually, you kind of flip your 0 and 1 handles with 3 handles. And you get kind of the green compression bodies. Anyway, we can just kind of glue them together. Schematically, I'm drawing kind of as a straight line that kind of bottom surface are that, and then when I attach on handles, I'm getting something of like a higher genus. So I draw those things with these kind of wiggly lines.
So should I think of this compression body as a coordinates between two surfaces?
It is a coordism between two surfaces. It's a coordism of a particular type. It's a coordism obtained by essentially just attaching 0, going from one surface to get to the next. You attaching a sequence of 0 and 1.
The genus may increase or decrease.
Yes, the genus will not increase. I mean, you may connect some components, but it's going to the standard issues that it's. The reason it's called a compression body is the idea that kind of the cores of the 1 handles have these discs that you can cut along until you're left with basically just a product or a handle body.
Still be confused. So if the genus if the genus keeps increasing, you have to come back, right?
Yeah, well, so it increases this way and then it decreases. Or I guess I started drawing my flow like that, so I had to turn my arrows around. Actually, going this way. But this is a lower genus, higher genus, lower, higher, lower, higher.
That's what you call code.
Sorry.
That's why you call code.
Yeah, that's why I color coded it. Because the pink are the compression bodies using the 1 and 0 handles, the 0 and 1 handles, and the green are compression bodies using the 2. And I am including the 0 and 1 because if you're doing it more generally, you have these kind of funny. You might have where this compression body that you want to think of is disconnected. Maybe it has a handle body. Like just generality, you might have a handle body component. And if that handle body component necessarily has a 0 or 3. But the thing is that this affords you all of the tools of Hilbert splitting. And all of these kind of techniques from low-dimensional topology where you don't have to worry about flow lines or getting actual functions to match it nicely. You can just kind of deal with all this well-developed theory of Hilbert splittings and generalized Hilbert splittings. And I think it was in Fabula's thesis where she really started developing the ideas of circular Hilbert splittings and generalized circular Hilbert splittings, thin position circular Hilbert splittings, kind of translating all the work that had been done for just regular generalized Hilbert splittings. And so, well, the point is that, I eventually wrote that paper. I guess the preprint came out in 2020 and it just got accepted the other recently, I don't know, months ago. But, the point is that you actually do get this here. And I'm just going to very briefly kind of say what's happening the idea is that Fabiola's work, where she deals with this idea of this kind of thin position and this kind of locally thin position. So if you know about Hagar splittings, basically the idea is that all of your thin surfaces, which should be kind of the which corresponds to these guys, the ones that are smaller. So you can kind of arrange this where each of these surfaces are actually compressible surfaces. And then each of these bigger ones are what we call strongly irreducible. And then the nice thing is that strongly irreducible has this kind of, while they're not incompressible, they have this kind of sense of being like they want to be compressible. So that allows us to start doing a lot of nice things with intersecting with other surfaces. And the point is, once we have it in such a position, that gives us enough where we're able to kind of straighten up that summing analysis. Because in general, if you're starting off with some sort of thing, this thing has been kind of wobbling. Also, how is it structured with respect to the Morse function? Well, using this kind of locally thin, we're going to spread it out to get all these incompressible, strongly reducible, very incompressible, strongly reducible. That allows us to say, oh, I can straighten out that analysis. Kind of like unravel this hair plate into this big mess. And actually, when you do that, you might be looking at the Morse function, circular Morse functions where you increase the Morse. But the trick that I noticed, and Fabiola did a lot of this work actually already. But the thing I noticed is that in fact you can do some extra kind of counting tricks to show that you can then kind of start squeezing things back down and recover actually a function of the original Morse-Novikov number you wanted. That while preserving the fact that the hand is straightened out, and that's giving us this, the extra balance. This entire thing worked really because this annulus kind of had, on your circle value Morse function, that annulus kind of had some wrap. It wasn't kind of level. Wasn't kind of the function wasn't. It actually had circle value Morse function is non-trivial on that. And so what we can actually do is that exact same argument basically allows you to say, well, look at any situation where you have an annulus that does that, and you can kind of do a similar decomposition. And so one corollary, basically following the same argument, is that if you take a knot and you look at a cable of the knot, basically running a torus model along that cable, it has the exact same Morse-Novikov. So that's a I was kind of surprised that Morse-Novikov numbers can change by cable. Satellites, it's not so clear on satellites. I'm actually having this full torus. So I want to get to the last part of our work here, where we're talking about these extra bounds. So this is the work that I've been doing with Fabiola. And briefly here, we have these extra concepts of a tonal number. And roughly what that is it's, up to adding on an appropriate constant, it's just the Hagar genus of the link exterior. And envision it the right way, it's what we might call like the Morse number of the link exterior, or maybe you could say the linear, if I want to make the distinction between circular and linear. Here's roughly the picture. I've got all of these coarse boundary points. I want to think of them all as the top of my manifold. And then I have this kind of Morse function over. So now I have a handle body bracket of 0, handle, and then a whole bunch of like one handles attached to it. And then dually, then I have all these kind of two handles that are unique with the giving me this with the rest of it. So the tonal number is really basically saying what's the fewest number of two handles that I need for this, or let's say otherwise, just drilling out arcs from the manifold to that way. The Hagar genus is the genus of this kind of completely blue surface, and the Morse number you might say is just kind of adding up the overall such presentations, adding up the minimum number of credits. So notice here, you do need to have. Just because this is a handle line in this case. So this is not a circle.
Just to make sure. So you're saying that any link complement serial can be put in this form?
Yeah, any three manifold boundary. And so a Haggard splitting is just for a closed manifold, it's just a decomposition of your manifold into two handle lines.
Right.
So for the tunnel number of a manifold with boundary, just basically says just start drilling out arcs from your manifold until you get down to a handle line. That drilling out arcs is basically kind of all this stuff. So I'm kind of drilling out this green compression line. But
What if I, maybe stupidly first fill in those boundary components with solid chloride and then look at the heterogeneous of that closed limit?
yeah, it's funny that could actually go down. So for instance, you take the link in S3. Well, the Haggard genus of that manifold is S0.
Yeah.
But it's actually a very deep problem in this kind of vein filling, this kind of filling that we're talking about, is understanding exactly when the Haggard genus can drop. So that's another story I'm happy to talk to you about. But that's
It depends on the frame, right?
depends on the framing, but so it's one of my favorite problems. Like when we're looking at this S3, there's one slope where that genus can drop dramatically. Can there be another where it drops dramatically? Nobody knows. Conjecture is no, but there, no.
Generically, it's okay.
Generically, you expect, very generically, you expect them all to be the same or at most level. And we can say a little bit more. Then there's a finite number of other slopes where it might drop by more. Yeah, I'm happy to talk more about that. That's just a little farther afield. It's a deep problem that has a lot of connections to big conjectures. Yeah, so right. So this is current work in progress. Today is written up, and this is just a glimpse of what it is. Maybe it doesn't seem as strong. So Pagino actually had a paper where it shows this inequality, that twice the total number of, let me just restrict to knots because there's actually a constant that I have to fill in. So Pagino actually showed that the Morse-Novikov number of the knot in this 3 is bounded by twice the total of that knot. But he used basically a Morse theory kind of proof. And he had asked Fabiola, is there like a geometric constructive proof? It's like you do circular Morse functions or circular Haggard splittings. Can we see this result from that perspective? And Fabiola and I started talking about it, and we're like, well, of course you can. And roughly, let me just very quickly sketch this idea. I've kind of got this decomposition here with the same kind of color scheme of the tunnel number. So I have this like Haggard genus, Haggard surface here, splitting this green compression body. The red is meant to be a okay. And then the trick here is you want to find a cyclic surface F that has some nice properties. And it's kind of all about how it's intersecting with this compression body and the sample body. So there's a little bit of work to say why you always find a cyclic surface. But then once you find that cyclic surface, you can basically take your same cyclic surface F, and then I'm going to do what's called like a normal curve sum. Just kind of like together. I'm just going to follow the F, go around the original Haggard surface, and then I'll connect it. And that's going to give me my thin surface. That's there, and the number of critical points for this equals the number of critical points of this presentation. Therefore,
We have a question on Zoom.
okay,
If
yeah.
you want to approach it, we typed it in.
Let's see.
How do you form a circular Morse function? Is not the ordering and, isn't the ordering critical to the construction of the Morse functions? Yeah, so, is the,
Well, the thing is, so if you look at a fixed presentation, so the question is about like, when you're looking at this circular function. I have to go back. You know, here I'm looking at a particular presentation, but I'm allowing to look at all circular Morse functions that are homotomorph to this particular one. So that allows to change it every quarter. And that also allows you to kind of, that's what allows us to sometimes cancel zeros, ones, and that allows us to maybe kind of pull some things apart. The analogy you should really think, if you're familiar with knot theory, is the difference between bridge position and thin position. Okay, so thin position, you're taking the bridge position and then kind of pulling it a little tighter, where you can pull some, minimum past the maximum. And it's the same kind of thing. So that was one question. The tunnel number, really quickly. Tunnel number is like a linear Morse function. So we're just got this map of R where I'm asking that the entirety of the boundary is at the top. So, and then we of course minimize all of that. So roughly tunnel number is counting that. Let me figure that out. The idea is that effectively it's this kind of linear Morse function instead of a circular Morse function. So this here kind of is kind of, we did that up around. If you actually look at what Patrick Monk did, you can actually start to see that in fact we're kind of actually doing the same thing. But we're like, well, we got to talk about why not the board? And there's this basically the idea what we can do is I can kind of just add a little collar of our link to the green compression body, but then and that's going to not affect the fact that the top is a nice compression body here, but I need to make sure I can get the green guy to be a compression body. Get it. Once I add on this collar to this little bit, that changes up. So I actually need to make add on next to another panels. Then we have to go through and structure accounts and actually what is it here. Point is that we can get actually what ends up being so this is what I'm doing is I go from circular unit splitting and I'm wanting to get one of these linear unit splitting. The point is that we end up seeing that this bound ends up being this kind of twice its own number thing minus what I'm going to call the Morse-Novikov genus or not. So what do I want that to be? For a knot, this is just the minimum genus. So G being genus, like a regular cycle genus. Among all of these, among all presentations that realize the Morse-Novikov number K, I want to look at the kind of minimum genus level set. So these level sets are cycles. Some other little technicality. Yeah. So we have this funny thing. It's not the cycle. It's not necessarily the cycle. So whatever that number is, whatever this minimum is, that gives us kind of structure of the way down. And as a corollary of this theorem, one thing that we know is that because there's a nice create a family of genus 1 knots that have increasing tunnel number. So that allows you to get a family of ones with the regular cycle genus 1, where either the Morse-Novikov number of those knots is increasing, or this kind of Morse-Novikov genus is increasing. Quite frankly, it's got to be this to make sure. I would expect it to be this one. This is kind of our question earlier that relates to this issue about wrapping. In fact, is it actually true that the cycle genus is this Morse-Novikov? Is there always a circle value Morse function? Is there always a circle value Morse function realizing a Morse-Novikov number, which has a minimum genus cycle surface as a level set? And yeah, I think that's a surprisingly difficult question.
So you know one of the inequalities?
I'm sorry.
The bottom question, do you know an inequality?
Oh, well, I mean, so this is a minimum overall, minimum genus overall set. Yeah. So we know like this is less than or equal to this guy. And that's because this is a minimum overall cycle surfaces. And this is a minimum overall cycle surfaces that are level sets of functions for realizing. Yeah. So I think this is like kind of key towards trying to take results about what you might do for vibrations. I mean, this is true if you add FT as cycle. And I think this is key for trying to push results about vibrations, or this is a key step in pushing results about vibrations to results about modifiers. This is kind of one of the interests for it. The other is it's just kind of a natural question that seems like it's obviously, of course, some ideas.
Is there a way how to compute it, like on the computer? So
Yeah, so in certain situations, so yeah, no, that's a great question. So the question was, is there a way to compute this number here? And and let me just say there's some ad hoc methods. One is to classify. So part of the work I had done previously, here, showed that surface. Shows that this is always realized by an incompressible cycle surface. So we can prove that this is always realized by an incompressible cycle surface. But there are knots with incompressible cycle surfaces which are not minimal genus. So one strategy is to say, can I understand all of the minimal genus cycle surfaces? Can I understand all of the incompressible cycle surfaces? And sometimes you can show that, oh, there's only one. Maybe you can show that there's actually only two. Maybe you can show that there's several, and you can still compute their, do some other tricks to calculate their. This is something we're looking at. One way of trying to approach this problem is looking at the Kaplan-Meier complex, which is basically has the minimal genus complex and the incompressible complex, where basically a vertex corresponds to the cyclic surface, and you draw an edge or make a higher simplex when you have each of these cyclic surfaces. And then, we are over time. Well, let me just say, wrap up here then. The last thing here is that you can also just kind of do the thing in general. So if you want to think of a link exterior, think of a two-component link. I have this little asterisk to remind myself to say, if you want to think about a link, you might want to think about links with linking number 0, say a two-component link with linking number 0. So there's a little slight funniness that can go on. For instance, when you might say the light, you're trying to think of the overall general function. There are ways around it, but let me just kind of point out that there's some funniness that we kind of recognize. But the point is, you have the same kind of business that we had sort of when I was looking at the toy model of knots and thick toys. So this Morse-Novikov number, say non-zero classes, we have this bound. In fact, you can think of this happening at 0 class, be like the linear thing, the tunnel number. In fact, if I just take any non-zero multiple of this class, you're kind of still, it's like kind of just wrapping around the circle the same way. More times. You can actually show that, this function is constant on raised in H2. And then maybe we similarly have a local maximum. So this function, this property really comes from, maybe there's a way to see it, but the way we saw it, it actually came from our approach towards reproving down the tunnel number on the Morse-Novikov. And then we can also notice that we have that this thing is zero exactly when size of the fiberglass. Now, this has lots of interesting properties, and I think one way to start puzzling about it, to think of a question about is like, how is this related with the first one? Right? What happens? Is the Morse-Novikov number constant on a face? The natural function. And we have some examples in evidence for that. Yeah. Anyway, I'll end here because we are over time. Thank you very much.
One more question about the last point. So do you understand the unit ball in the Morse-Novikov law?
But we have to be careful. I mean, I probably should have, so I wrote X and then, and it's not really.
Semi-norm. It's a
Yeah,
spell,
I mean,
but
no,
first one
let's
is also
not even worry about that semi-norm. I mean, it doesn't. Yeah, I mean, I prefer to think about it as like, on the circle, you just have these vector values and it's locally maxed. I know what's happening on fiber faces. Right, so I know it's always 0 on those fiber faces. And then, but, and I have this locally maximum property.
But do you have at least a containment the way the Thurston norm is contained in the unit ball in the Alexander norm? Ball?
So yeah. So this being the point is that we don't really. I mean, yeah, so I was being only very precise and suggestive. So this guy here, I want to think of as being basically this guy, but instead of genus, I'm looking at negative order. Right? And so in that sense, there's a natural bound because we still have the same equality. That's the right answer. So you can ask about the same question about this minimize, what is the Euler characteristic of the surface? So the point is we have that natural inequality. The same way that we have the natural inequality.
At least for non-complements, but for
No, but it's the same thing. I mean, yeah, it kind of this what happens to non-complements is just a model that actually happens more generally. Like the first norm being negative characteristic of the surface, the minimum negative characteristic of the surface representing that class, and this I want to think about the minimum negative characteristic among surfaces representing that are level sets of blah, 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 blah.
So then you get a containment.
Yeah, you have a natural bound. But I'm not really as clear on the properties of this function. This function is different than this function. So this is like our circular bridge number, and this is our radical number. So I would like to understand this a lot.